it's me again. Actually, it was unplanned, and unfortunately, Giuseppe Longo could not come and told me on short notice that he cannot come, so I thought I'd jump in before we have a longer break, allowing everyone to have a coffee outside. So as I said, it's a short break. We will have dedicated coffee breaks, but today we thought 45 minutes in a row without a break, and the next slot of 45 minutes might be a little bit too much. And so we thought, give it a short break. So today it's my pleasure to talk about machine learning in astronomy. And in principle, I want to talk about the lessons we learned from learning machines. And yeah, as George already elaborated well enough, the data sets in astronomy are not just big. They really show complex structure in the spatial domain, in the spectral domain, and also in the temporal domain. And those are the things we are interested in. But those structures appear to be so complex that on top of the huge size of the data sets, it makes it really, somehow impossible to really find those things. And there are things like heteroscedastic noise, the heterogeneous data sampling we have in time series, a lot of things we will hear about during this week that make astronomy, especially data science in astronomy, so complicated. So let's first start with regression problems in astronomy. And as an example, photometric redshift estimation. And so the analysis of these large catalogs now demands an efficient solving of so-called regression problems. And it's very simple. We have some kind of model where we put in some features or data, and we want to estimate a certain value. That can be a lot of different kind of values. It could be important properties for dedicated objects we need to do our research, and for example, it could be something like redshift, where we want to see how an object is shifted due to the Hubble flow with respect to the wavelengths, the rest frame wavelength in laboratory. And in this example, you see two quasars, one high redshifted with 3.8, a redshift of 3.8, and a even more high redshifted quasar. And you see underlying the filters. You see the filters of Sloan, because Sloan was the first big survey providing photometric data and spectroscopic data to such an extent that you really can build sufficiently large training sets to really run machine learning applications on that. And so with this, the regression problem is now you don't have the spectra, you just have images. And now the question is, which of the tiny red blobs is actually the one at 3.8 and the other one at 5? And why you want to do this is actually because we cannot afford to do the detailed analysis. It's really too expensive, because if we want to take spectra, ESO could provide, or other big institutions could provide telescopes, but we will never have enough telescopes, it's astronomy, we never have enough instrument, and definitely not enough observation time to fulfill all the tasks we are interested in astrophysics. So what can you do about that? And just as introductory talk it's meant. No, it's very simple methods. We do it more complicated, but those simple methods already are a good indicator of what makes it so complicated. Nearest neighbor models just are local models. They just look in the vicinity, in the neighborhood with respect to your high dimensional feature space. They look what's in the vicinity, what are the properties of those objects, and then you try to derive what are the properties of new unseen objects. And if you want to deal with missing values, you just change the neighborhood function to deal with missing values by replacing the missing values with some kind of approximation, some bias or prior knowledge you have. And if you now take such a very simple example and apply it to the data I've shown, Sloan data, DR7, quasars, and you want to estimate redshift, and you take the usual features, you end up with the usual plot where you see the spectroscopic redshift. We consider the ground truth, even though there's also some variations in, also caused by the spectroscopic pipeline of Sloan doing the fitting. And we have the estimated redshift, and the estimated redshift is just based on photometry. So you take pictures, and you use a photometry of objects to derive those estimates. It's very trivial and simple, I know, And you can do certain, back then we did certain error analysis and checked how is the error distributed and got some measures. But what is science about? It's actually about challenging others and trying to compete with others, being better than others. And back then we read a publication by Omar Laurino, and we saw the results, and in principle we were shocked because they were better than we are. And of course that's a frustrating moment when you think, okay, it's a simple model, it's simple data, they use exactly the same data and they are better. What happened? And we read it and, oh no, they are not using exactly the same data, they flagged out some objects. That's really tricky in astronomy. How do you do things in a reproducible way? How do you share data sets so others really can validate that their method and their algorithms are performing better? And when we changed the data, it improved. Yeah, yeah, we are better and we are closer to it. But then we did a detailed analysis, we read the publication over and over again and figured out, oh, they're actually using more than the standard features back then. And what they did, they used some error measures. And then we thought, oh, not all of the features are useful, so we have to test different combinations. And that's what George spoke about. Yeah, then it's exploding. Then it becomes so untractable that you cannot easily figure out what are the best 4 out of 55 features. You end up calculating 340,000 combinations of features for a simple question. You can do everything, but not everything you do is useful. So back then, we had a code, and evaluating one model took 100 seconds. It was efficient Python code on a decently large data set, so improved the data set, did it on parallel. Fabian Giesecke, who is here starting this afternoon, we worked on this and presented the speed up, and we really managed to speed it up tremendously by using GPUs. Before that, it would have taken us 395 days to evaluate all 340,000 models or questions or feature sets. Now on the GPU, it took 3 hours. So it's affordably quick. With new hardware, you can do new stuff you never thought of before because it's hilariously parallel. And when you do so, you can now evaluate the median absolute deviation and the root mean square error. Both are meant as measures of quality of your model. You can do it for all objects and you end up with this cloud representing the results of all 340,000 runs. The blue one are the classical features. The red one are my favorite ones because those are the features you never should use. Because if you use those features, you definitely get the worst result. But of course, if you go to the Pareto front and optimize it by visually inspecting it, what you see is, oh yeah, you really can build great models. And we put a lot of effort in feature selection strategies. Antonio will have a presentation on his work done in this direction. And features, selecting the meaningful features. What are the features containing the knowledge? That's essential. And Antonio, just as a quick preview, will talk about something he did for a lot of different feature sets and how he used techniques from genome analysis to visualize actually what he was coming up in his upcoming talk. But the lessons we learned from this simple feature selection experiments is what we store in our databases is actually not what we need for machine learning. What we have in databases is in most cases features we traditionally developed to mimic our eye, to mimic what we see when we inspect stars with our eye on the sky. And that's why we ended up with magnitudes. And of course, if you take an image of an object and fit a point spread function to it, and you end up with a magnitude in 5 filter band and errors, that's it. You compress 10 by 10 pixels to a single value. And of course, you are losing information by doing so. And the challenge now is, how can you deal with this? So we really have to reconsider what we store in our databases, and we really have to think what machine learning demands to do efficient stuff. And yeah, I think also something you already touched, George, uncertainties. It's so important that we try to be precise by being imprecise, by using the uncertainties provided correctly. And meaning correctly means now using them in proper ways. And what we want to do is, we still have, as an example, the simple regression problem. But now we have all the uncertainties that come in as our input, measurement errors from our catalogs. We have uncertainties in our model. Is the data set representative? Is the way we modeled it the correct way of modeling it? Many things that influence it. You had longer number of those things. But what is absolutely clear is if we have uncertainties in our regression models and our way of solving them, then we have to have uncertain estimates, uncertain results. We cannot predict a single value if we can't do so. And the point here is, in principle, we want to go from a point estimate in Redshift to something like a probability density function that expresses what it is about. Of course, we do it already since a while. And the reason for that is we have multi-modalities. This is now an example object taken from Sloan. And if you see, the true redshift is the red line. Those are the nearest neighbor values. And if you would use, like in the equation stated in the beginning, just the mean over all neighbors, you end up somewhere in the middle. And as you can see, it's either that or that. That's what the correct answer has to be. And therefore, as a simplification, if you now want to evaluate your PDF, I've seen a lot of publication where people generate PDFs, but they evaluate the quality of the PDF by just taking the mean value of the PDF and checking how well does the mean value of the PDF fit to the actual value. And that's in principle saying, okay, this is the mean of the PDF and I compare it to this one. Even though in this example, in this simple example, you would say, yeah, it's on one of the bumps. The likelihood is quite high. You have to consider using the right statistical tools. And using the mean is probably not the best choice. And it's the same for Euclid. I read some publications where they developed the concept of stacking PDFs. Stacking PDFs of multiple objects to figure out how many are within certain margins and coming up with own statistical error measures. And as you can see from this very simple example, if you have several models and you co-add them, then becoming narrower and narrower. In this case, you have one guess that's above, one guess is below. Even though the likelihood in both guesses is fine, the stacking will result in something where it's okay, even though the likelihood is close to zero. And in the case where your estimate was always on one of the bimodal points here, yeah, you would say, yeah, it has a huge fraction of outliers. So really, we have to question the tools we are generating, and we have to talk more to people from statistics on that. Proper evaluation tools are around. In weather forecasting, we learned from Tillman-Gneiting, they use a CRPS, a continuous rank probability score, and it's something that captures calibration and sharpness of your prediction. So it tells you really how accurate are you with your prediction and how well is the shape of your prediction formed. And if you do so, you calculate it by using the cumulative distributive function and calculating the integral between the Heaviside step function, that's a cumulative distributive function of the true value, that's a step function, and actually your prediction. And the integral area is in principle squared and reflecting how well your estimate is. If you think about it a little bit more carefully, you see why this is a much more powerful tool in evaluating it, because it tells you more how it's distributing stuff. Another proper tool is using the probability integral transform. And the probability integral transform lets you see whether your predictions are with respect to your deviations from the center of the object under-dispersed, so you are too spiky in your prediction. You are predicting a too high accuracy in your PDF with respect to your actual accuracy. And you are over-dispersed if you just say, yeah, tomorrow is 20 degrees plus minus 20 degrees. I'm always correct for most days in Germany, but it's quite unprecise. Or you are biased if you're always over or underestimating stuff. So you want to achieve something that is reflecting good calibration. So if you now use k-nearest neighbors again, and in this example it's that you use a single Gaussian placed at the mean of your nearest neighbors, and you give it a sigma of 0.001. So you make it a point estimate in principle. A very narrow Gaussian is what you predict with uncertainty. You see you are extremely under-dispersed. You see that you are either on your CDF at a 0 below or at a 1 above, because the function is really steep at that point. And in principle, the CRPS is quite bad because you are lying. You are lying concerning accuracy. The next thing is you could say, oh, let's take a wider Gaussian. And as you do so, you see the CRPS and the PAT improves. But it's not correct because it's not a uniform uncertainty you can apply to every object. So what you do is you just calculate the sigma, the standard deviation of all your nearest neighbors, and you come to a point where you start to improve. You see, it's successive steps thinking about how to add uncertainty. But as I said, we have multimodality in, and the problem there was a single Gaussian can't do the job if it's a multimodal problem. And here in this example, we fitted 6 Gaussians to the data, and if you now do it with a multimodal system, you end up with plots that look like that, where the CRPS is definitely much better, and the PAT gets to an order of being well calibrated. Nearest neighbors at a certain point has shortcomings, but there are other models like a random forest or a certain kind of neural network, a mixture density network that predicts as output the parameters of a Gaussian mixture model and therefore learns how to predict multimodal distribution in this case. And that are steps making it better and better by adding the uncertainty correctly and having a proper tool that is something like a truth theorem. You cannot say you are extremely precise if you are not. You can only be as precise as you actually are, and if you are not, your score will drop. And now, yeah, it's all about deep learning and the silica brains coming into business. And of course, if you now see those approaches that were feature-based, we presented, or you presented last year at Astroinformatics, something where we combined this approach with deep learning. So we had some deep convolutional layers and used the mixture density network to create those predictions. So we don't use features only. We take imaging data now. And yeah, the VO is there. And I must always say, God thank that the VO is there because we have a source for data. Even though as soon as you start downloading data, you figure out, and Erica, so see her poster, can tell a lot of stories about using VO services to retrieve data, it's sometimes still a pain. And we are ahead of other disciplines. So even though medicine might pay you more, I would suggest not to go there and stay in astronomy. So at least we have a standard, a fit standard. And yeah, so you can make use of the VO standards and the VO tools that are around in order to extract data. And what you need now is you need images per object. Of course, you need much more data than you had before with the simple features, where you extracted a set of features per object. Now you want to extract images of those objects, but you can do so. And if you put those data in, and now please note we had to log the sum probability density in this plot. That's why it's looking wider, because it became so accurate that in the other plot, not logging it, it appears like a line, a straight line, because it's becoming better and better. The system automatically adopts and learns how to extract the right features from the imaging space and learns to create a well-calibrated, by adopting the loss function of the training, a well-calibrated output as a Gaussian mixture model. And by doing so, we could further improve it. And actually, at a certain point, we came up with actually what science is about. Because if you only use quasars for training and you only predict on quasars, it's cheating because it's already depending that your classification worked well. But for some objects, you cannot deal with those classifications easily. And a red faint star appears to look exactly like a high redshifted quasar on photometric space. And we will soon have cool Gaia data available, making it much easier to get rid of the faint red stars. But up to then, the idea was we take in galaxies, we take in quasars for training, all objects with a redshift, and we put in stars and just assign a redshift of 0 to stars. And then the system automatically learns in one run to do actually classification and assigning a probability for a redshift. It's now just solving the question of what is actually the redshift. It doesn't care about the type. It's just saying if it might be also look like a star from the data space, the probability for being a star, redshift 0, is similarly high like for the other ones. What is fun, of course, if group members want to know how old you are and you know that redshift is related to age, then they take your picture. Antonio was so kind to ask the question, how old am I? Put my picture in the same machinery and came to the point I have a redshift of 1.7, so that means I'm 9.3 giga-years old. I think I'm still fresh and young. Rotten dead fish, of course, has a redshift of 0.3, and it's just 3.5 giga-years old. And that's obviously true and correct, as you can see, because fish does not live as long as humans do, and therefore rotten fish must be younger. So the important thing there is really, if you feed shit to a system that was not trained to deal with this, it would result in crappy results. So stupid stuff in, stupid stuff out. And that's really a challenge when you use those deep learning stuff, to understand those things in detail. So the lessons learned... Yeah. Well, that's why I'm sometimes behaving like a little kid, I know. No, absolutely. And for the lessons learned, at that point, I really want to say uncertainty is really essential to further improve our science quality. And we have to do it in a proper way. And therefore, we have to start working closer with statisticians to learn about proper tools of evaluating stuff. Of course, we can come up with clever ideas on our own, and we did in the past, but sometimes it's easier to bridge to other communities. So let's quickly run to morphology. Morphology is the other big question, how to deal with different shapes and structures. And what I did back then, I used a human brain for unethical experiments. It's my daughter Eva. She went to school first time last week, Thursday. At that point, she was 2.5 years old, and I gave her a very simple task: put the brick in there, and guess what happens? Some might know this movie, and I say, Eva, put it in. She puts it in there, and the problem is the shape has 3 squares and just 2 triangles, and I was pointing her there. And that's what we do in physics. We are biased by our assumptions. We already know how the world looks like, and we do not allow people to come up with own clever solutions. We don't give the computer the freedom to do what they should do. And in principle, the solution is very simple. We need experts to inspect all the data. But seeing the exponential growth in data, and seeing, I wouldn't even talk about the linear growth for astrophysicists or astronomers, so it's not possible. So we need the combination of the human pattern recognition capabilities supported, as you already said, for the visualization and the other stuff, where computers help us, pointing us to the right spot, that we can spot what we can spot, and we can come up with some interpretations and do those things. And dimensionality reduction is such a tool. We map complex structures from a high dimensional space, the image space, or spectral space, down to a low dimensional space, a 2D or 3D grid in this example. In the past, we did a lot of experiments, used different dimensionality reduction techniques to achieve it on different data sets, local linear embedding and isoplanar mapping, and tried a lot out of the box. But the challenge when we were faced with data from radio galaxies was, there's this stupid rotation and flipping invariant. For a human brain, somehow it doesn't make a problem to turn a piece, and brute force just means pressing harder. And so the challenge was come up with a rotation and flipping invariant thing. And we tried a lot of clever things, and in the end the most stupid thing worked out. We just use GPUs and just calculate for all possible rotation the pixel-wise Euclidean distance, minimize it, and therefore determine the best matching angle. It's stupid. We tried network. We tried meshes like for face recognition. We tried a lot of clever stuff. But this one somehow worked out better for some things. And if you now take those simple bricks Eva was faced, so simple toy example, and in this example, those pictures are representing a set of, I think, 10,000, 2,500 each, of noisy, little noise in it, little differently rotated images. And to explain what such a self-organizing map is doing is, you just find the spot where you match best, and then you change this object and the vicinity, as marked here, to look a little bit more like your example. And you turn around and you figure out where you match and you place it and you find the next one and you change it and you place it. And you give the computer just time to evolve. And over time, the map evolves, it organizes on its own, and in the end, you end up not inspecting as a human 10,000 images, you just inspect 25 images. And by inspecting 25 images, you can say we have squares, crosses, ellipsoid, and triangles in the data set. That's all you need. And this is a simple algorithm, but it's a nice algorithm to visualize because you easily can create movies. There are really a lot of powerful tools out there to do dimensionality reduction. But by doing the dimensionality reduction, you now project your complex data into a space of shapes, a space of structure, where coordinates in this projected space reflect how things look like, morphology-wise. You don't have to fit complex structures, you just take coordinates, assuming a certain function for your projection, and can use this as basis for your classification. So, if you run it on real data, and somehow, as you could have figured out, I like pink, because pink stands for parallelized rotation flapping invariant Cohen maps, an obvious acronym. And actually Bernd Doser is in the room as well. He was a person who actually wrote the ultra-fast GPU code we are currently using for all our scientific runs. And you can use it to create such a map. And if you do such a map, somehow it's stuck. No. If you do such a map, you end up with a large map. And on this large map, you can start looking around and identify certain objects. You can go into details and inspect objects in detail. And Raphael Mostert, I think, is showing a demo on what he did during his master thesis, using also some kind of dimensionality reduction and a service for loafer data, actually. It's another way of explorative access to your data. And what you can do is you start annotating. As an expert, you don't ask volunteers on the internet to do a task. You ask the computer, sort the images based on their morphology, and then as an expert, you start inspecting, and you say, those are single compact objects. And by saying those are single compact objects, you are representatively, in this case, it was data from radio galaxies you used. You deal with 120,000 objects because 60% are boring point sources. And please don't inspect 60,000 or 120,000, 60% of, don't inspect 120,000 boring point sources and always click point source, point source, point source. That's killing brains, and that's not what we are meant for. We are meant for the clever task. And with those results, we just can easily create so-called heat maps and figure out where objects match best. And for this object, I see it matches best in this region, and it's annotated as doubles. Oh yeah, it's a double. And that's how you can transfer knowledge. And Tim Galvin is actually giving a talk on what he did in the direction of transferring labels and dealing with multi-wavelengths things with dimensionality reduction approaches. So it's really a powerful tool, understanding what's in the data without inspecting all the data sets. As George said, most of the data will be seen by computers. And we as humans should only see those objects that are really interestingly new and show interesting stuff. And you can look for outliers by looking how well they are represented by the prototypes. So a lot of techniques exist that do outlier research without dimensionality reduction. There are a lot of powerful tools out. We just have to start employing them and using them to get back to the interesting parts. And yes, that's a quick view of, I don't know what it's currently looking like, of what Raphael did. If you now create a web service, it's better than the way of accessing archives nowadays, where you have to type in explicitly certain criteria that were extracted. You can start scrolling around, you select and say, give me all objects that are similar to this one or that one, or you say, I'm interested in certain regions, and that's helping and changing the way of discovery and the way of getting the objects you are interested in. You don't have to set up a Galaxy Zoo or Radio Galaxy Zoo, a Zooniverse project for every single question. No, you can do it on your own. And you don't have to come up with specific questions every time. You can do it on your own with specific questions. Another example for dimensionality reduction, Alexander Becker still remembers, I guess. We were playing with data from Magellanic Cloud, and I was invited to a conference for star formation history and had no clue about star formation history. I just know they fit weirdish stuff I don't understand to, based on theoretical models, they fit data to HR diagrams. And if you take a HR diagram, it's giving you a color versus a magnitude and telling you how many objects are in a certain region. And what we did, we just transferred this into a coarse representation, a number density plot, a Hess diagram, where you just reflect how many objects are in a certain region. And when you use this now as basis for a self-organizing map, you just have to account in the neighborhood, in the distance function, that the number of objects per stellar cluster you want to analyze, because we are using open stellar cluster with their HR diagrams to see how the main sequence looks like in order to understand how the age distribution of stellar clusters over the Magellanic Cloud looks like. And in principle, what you do is you now just run the same mechanism, and it takes a while to evolve, and you see it's automatically structuring and clustering different stellar clusters around the from the HR diagram. And in the end, you end up with a map. The question is, what is it good for? Absolutely nothing, the older ones of us would say. And it's good for using weirdish color over plots, like George mentioned, coming up annotating stuff, and color is probably the poorest choice. So making the x-axis the coordinate in the space of shapes, in the projected space that is reflecting morphology and shape. Making the x-axis green, making the y-axis red, gives you a weirdish color gradient. I apologize for those not seeing the differences in there, but if you reproject it to the Magellanic Cloud, then you see, at the front you have a certain population that is yellow, and if you look back, you see it's a younger one. It's actually the shock front where the Magellanic Cloud moves through the intergalactic material, and their star formation is triggered at the front. And there was actually a publication, I don't know by whom it was, they fitted isochrones to each of the stellar cluster and came to exactly the same thing. Of course, they had ages, but we could see the distribution by just letting the data talk for itself, by just using the data, putting it in a stupid algorithm, sorting it out, putting a color for a visualization on to visualize the correlations the computer found, inspecting them and saying, something is different, going back. Why is it different? They seem to be younger. Why are they younger? Yeah, that's the direction of motion. So turning around the way of discovery, not being driven by hypothesis, being confronted with some nice correlation and thinking about what could be the physical reason for that correlation, what is the reason for that. That's how it's somehow changing. And you could do it for the small Magellanic Cloud, but there you couldn't see it as clearly as in the other one. So another example for dimensionality reduction are data cubes. H1 radio data cubes in this example, taken from a region close to Orion. If you just take the whole data cube, each point, each pixel is an own spectrum in principle. And what you do is, if you want to present it in 2D, you just flatten it by integrating over each spectrum and calculating what is a combined flux over that position. And you end up with a plot that is not saying a lot. But if you now do exactly the same, you just take all the individual spectra in the H1 data cube, all of them, and you train a self-organizing map. Then you get differently organized shapes. You got double peaks, single peaks, triple peaks, sometimes shifted because it's not shift invariance in this case. Invariance is always very important to focus on certain aspects. Do you want to be rotation invariant for some spatial structures like galaxies? Yes. Do you want to be shift invariant for certain kind of spectra of objects where redshift doesn't matter? Yes. So you always have to think of how to add certain invariances to your algorithms. And if you do so and overlay a color plot and now use a color instead of a color code reflecting the intensities, you immediately see a huge bubble. back then the researchers were really interested in. They tried fitting Gaussians to each individual spectral line and tried to get it out, but it was not done spatially combined, just in the spectral space, and therefore you couldn't clearly see it. But with this, you can see it. And what you can also do, and it's all, of course, about visualization. What you also can do is now you can check each spectrum is now represented by a color. The color is referring to the prototype that is matching best to the actual spectrum. But there's still a discrepancy between the actual prototype and the actual spectrum. And this discrepancy you can express. It's very simple. It's a distance. And by doing so, you see the regions that are more turbulent. That's the Milky Way on the left-hand side. It's a turbulent, complex structure in there that are not well represented by the prototypes, and the ones that are smoother. So you understand actually those are regions where a lot of stuff is going on, a lot of complex stuff is going on. I still haven't understood, where I need some other computer-guided magnification glass to point me to the right spot. So the lessons learned there is, yeah, very important, as you saw with my daughter. Don't bias your system. Really try not to do so. We always knew in the past the best features for photometric redshift are the classical features. Colors of neighboring filter bands is what you should use. We learned, no, it's not. We already knew how galaxies in the optical regime should look like. They should follow the Hubble tuning fork. No, it's a nice approximation, but it's not correctly reflecting what it is about. In our brain, we like to come up with classes because it makes things easier to distinguish and to think about, but that's often wrong. We are often guided by pre-assumptions that might not be correct. So try to be less biasing your system. Use the stupid and very fast computers for the boring task and do the creative task again on your own. And finally, I always ask the question, because ESA asked the question for that galaxy. What do you see? Is it a dolphin or a penguin? Because they wanted to name the galaxy. Who is for dolphin? Who is for penguin? And that's the point. You did not listen. 37 minutes and 29 seconds. I tried to convince you, don't be biased, because it is a kingfisher. It's absolutely clear. That's a problem. We are all so biased in the way of thinking, and we are asking questions in precise ways. We often don't allow people to say, I don't know. Is it a smooth galaxy, or does it have structure? We should have a lever somewhere in between. And some objects, even experts, can't say whether it's elliptical or spiral galaxy, because the spatial resolution for some objects might be so poor that you cannot distinguish for those objects. And then the fair answer should be can't say. But if you enforce an answer, you create problems. So with this, I would like to close my talk. Thanks for your attention. I unfortunately forgot my closing slide with thanks on it. So thanks for your attention.